All right, let's get started a few seconds early today. Hey, everybody. So today, welcome to another week of fast book reading session. This is week 6. Last week, we looked at chapter 4 SGD, and there's the last bit that was left, there was just the optimizer bit that was left, but we covered the rest of the chapter and wrapped it up. So we're going to finish the optimizer bit, which is going to take the first 5 or so minutes, and then we're going to look into the chapter 5 pet breeds today. And I'm going to try and wrap up chapter 5 today as well. And after chapter 5, we'll go deeper into the computer vision, and we'll go deeper into the fast AI library. So you should be able to then, straight after this, you should be able to do a lot more projects in computer vision, especially classification, and you should be able to build stuff with your own data sets and of much better quality than what we looked at in chapter 1. So as is usual, because we're live on YouTube as well, I won't be able to monitor the Zoom chat, and I won't be able to look at the YouTube live again. But if you go to that link, 1db.me/fastbook6, so let me try and bring that up. Just a quick question. Can you guys see my Firefox window, please? Angelica? Or, okay, chat says yes. Excellent. Thank you, everybody. All right, so if we go to that link, the Fastbook Reading Group week 6, that's missing a poster. I'll add that later. And we'll also add, basically what we do is every discussion post, this is the same as every week. And what happens every week is by the time we finish, then everything gets a YouTube video. And this is where all our comments and this is where all our discussions are held. So if somebody is watching this in the future, they have a place where things will be persistent even after 6 months or a year from now. So that's that. So please go to that link, 1db.me/fastbook6. I'm going to paste that in the chat as well. 1db.me/fastbook6. And then we've also had another great week this week. I'm so glad to see regulars. I'm so glad to see Korean coming back even in week 6. And he's done it again. He's shared his logs, learning logs, and he's shared what he learned about stochastic gradient descent in our last chapter. So I'm really, really excited to see people who are doing it again and again every week. And I'm excited to see Ravi as well. Ravi's come back, and I really like the visualizations from Ravi, especially the one that we can see here about images models. It seems like he's gone in and added some effort and started creating his own visualization. So thanks, Ravi, for your effort, and thanks, Korean, for your efforts as well. And Vinayak's come back again this week, and he's also shared his week 5 summary. Something I was really excited to see. I think I kind of missed it, but there was this experiment that Vinayak you did about basically about having, why do we need deeper architectures? And that was, I guess, the gist of the question was, in theory, if you have one nonlinearity, then as per the approximation theorem, you should be able to approximate any function. So I guess the question you were asking is there any advantage of going deeper? And I just want to quickly address that. That's a good question that you've asked, and I'm so glad to see that you've been doing experiments as well. Just something that happened is my PowerPoint presentation got updated, so I don't have that experiment as part of the PowerPoint slides. But let me see if I can find it. Can you guys see my Slack as well? Yep. So I think that's these are the experiments in Slack in Fastbook. There were a few experiments that Vinayak's been doing, which I'm really excited to see. So I think one thing you'll realize as you go and start working with more and more models is that what works in practice, what you think would work in theory, and when you try it in practice, they're kind of sometimes very different. And again, this is one of those things where even in theory, if you could have like a few nonlinearities, that would work. But in practice, really having deeper architectures is what really works. So it's been done over years and years of research and over years and years of experimentation by top researchers in the world. And that's where this idea of having really deep architectures come from. So having said that, let's get started with our Fastbook session. We'll wrap up the optimizers. Because now going forward, every chapter is code heavy. I'm gonna basically use the PDF versions less and less because we're going away from theory and we're getting more and more into coding. So if the screen feels, if you feel like I need to zoom in or something, then please directly message me or just put it as a comment on the report. So I'll keep having a look at those things. So we need to first wrap up chapter 4. So let's do that. It shouldn't take that long. All right, it's loading. Okay, so that's chapter 4. So where we finished last time was we looked at the SGD and mini batches. Basically, it's like we go through the mini batches and then we pretty much put it all together in the sense that we calculate the loss and then we do the loss dot backward and we update the parameters by doing parameters minus equal to parameters dot grad slash LR. So LR is basically the learning rate that tells us how big a step we want to take when we're trying to update the parameters. So that was something we that's where we finished last time. But because this pretty much this bit, calculating the backward and then updating the parameters, that's so common that even PyTorch has a class for it, and that class is called optimizer. So something you could do is you could basically then create this very simple class called basic optim. And one thing you'll realize is whenever you create a model, which is a nn.module. So in PyTorch, when you create something like ResNet 34 or you create something like a ResNet 50, that's what goes into the training. It's in PyTorch, that's an nn.module. And what that has is it has parameters. So PyTorch makes those parameters available to everybody. So you can get the weights and basically the bias from this linear model that we were training last time. And you can see how the weight is pretty much a torch tensor and the bias is also a torch tensor. And because these parameters are available, what you could do is you could store them in a self.params and you could store the learning rate in a self.lr. So this is just basic object-oriented programming. Then you could, in terms of the step where every time you have to take a step in the parameters, you could just go through each of the params and you could update the parameter by doing p.data equals p.grad.data star self.lr minus equal to. Pretty much you're doing the same STD step. And then if you want to zero out your gradients, then you could go for each of the params, you could just say p.grad equals none. So that's zeroing out the gradients. So then what you could do is you could create your optimizer passing in the linear model with its parameters. And then your train epoch step, that becomes really easy. So you could have a calc grad function, which we saw last time. Let's see where that is. Here it is. So in your calc grad, you're pretty much just getting the predictions, you're calculating the loss, and you're doing the backward. So then what that does is now your parameters have gradients. So that's exactly what you could do. You could calculate the loss and you could do a backward passing in your batches. And then you can call opt.step. So instead of going for parameter, like if doing it manually every time, which is what our past train epoch loop look like, you could put everything in an optimizer and then you could say opt.zeroGrad. So even PyTorch, if you search PyTorch optimizers, torch.optim, it has already all of these classes. So you can create an optimizer passing in the model parameters and you pass in something called the learning rate. Don't worry about what momentum is right now. That's something we can look at later. But something then you do is you get your output from the model, you calculate the loss, you do the loss dot backward, and then you do the optimizer dot step. So that's a very, very standard training loop that you'll encounter in almost going forward in every training that you do. So that was pretty much it. After this, it's just some coding, like you replace that with SGD from the Python stocks, and that's pretty much it. And then you can put everything in a learner in FastAI. So FastAI has this convenience called learners that accepts data loaders, it accepts nn.linear, and you can pass in your loss function, which is what we calculated last time, was the mnist loss. So remember how the mnist loss was just pretty much looking, because we were doing classification of 3s versus 7s. So if 3 is on the left and 7 is on the right, then this MNIST loss is just trying to calculate the distance. It's like how far is the prediction from the actual truth. So we looked at this very deeply in our last week. And then you could pretty much call learn.fit, and that fits. So that's just the main thing. And then one thing you will realize is what happens is, and this is the part that I was talking about, is like you want to add nonlinearities. So if you don't add nonlinearities, then two linear layers are basically one linear layer. So in the end, what you want to do is, that was a very basic network that we were training. When we add more and more linearities, then we really want to go deeper and deeper. So you pretty much now, instead of having your model to be something like an nn.linear, the model becomes a CNN learner, which is something like a ResNet 18. So if I go, so you could actually have a look at what this ResNet 18 is. So I could go from Torch Vision. Sorry, I've tried to zoom in, and I have messed it up. 1 second, please. Okay, from Torch Vision.models, I think you import ResNet 18. That should work. Yep. And then if you want to really check the architecture, you could do something like that. And then that creates your architecture. So you can see how this architecture is really, really deep. It has so many blocks. It has so many nonlinearities, and pretty much it has 18 layers. That's what ResNet 18 stands for. So you could then create a much deeper architecture, and then you could call fit one cycle, and then you see the accuracy is like boom, because it's 99.4, because that's when you have a deeper architecture that for which this problem's really, I mean, it can fit and understand the problem pretty easily. And then in just one epoch, you're able to classify your handwritten digits. So that's where we finished last time. If there's any questions, let me just go to that report and let's see if there's any questions so far. So we've wrapped up chapter 4 by now. Oh, thanks, Angelica. I think you added the pretty much the slide here. So thanks very much for doing that, for adding the banner. Okay, so it looks like there's no questions. So that's where we finished chapter 4, and now we're ready to start with chapter 5. And in chapter 5, this is where things get really, really interesting. And this is where in chapter 5, we start with more real world problems out there. So we're going to look at the lost function in a lot more detail. So we're going to understand, on your left, you can see the table of contents. So we're going to understand cross entropy loss. We're going to look at the activations, what that means, and what softmax is. We're going to look at log likelihood, taking the log, and then finally we're going to go model interpretation. So from this chapter onwards, the one thing you will see is that we're going to go, it's going to be the same classification problem that we did in chapter 1. But from this chapter onwards, we're going to go deeper and deeper into that classification problem. So we're going to create better models from this chapter onwards. And to be able to create better models, we need to understand what an optimizer is in more detail. We need to understand how the loss function works in more detail. We need to understand what the learning rate is. So there's like this whole section on improving a model where we'll look at what a learning rate finder is, we'll look at what unfreezing and transfer learning means, and pretty much end up with more deeper architectures. And then by the time we finish this chapter. So I'm going to try and wrap up this chapter all the way today, and then also still have some time for questionnaires. But that's me being very optimistic. So let's see how that goes. But that's essentially what we're going to look at today. All right. So image classification. So this is just a summary of what we're going to look at in the next chapter. So we're going to do two things going forward. Is like we're going to make the models better, and we're going to apply the models that we've learned so far and everything that we've learned so far to a wide variety of types of data. So it's not just going to be handwritten classification or cats versus dogs, but from this point onward, you'll be able to apply this in knowledge to a lot more data sets. So in fact, what you learned from this today, you could then apply it even to medical data sets, or you could apply it to any data set that you want. So what we are going to learn today is going to come in very, very handy. So let me restart the notebook so that everything is fresh. The command for that is escape and 00. So that's a shortcut. So going from cats and dogs, so in chapter 1, when we started Fastbook, we created a simple classifier in 5 lines of code, which was a dogs versus cats classifier. But again, the same data set, what it does is it also provides pet breeds. So instead of doing cats versus dogs, remember where we looked at last in the first chapter, and we had a function called isUpper, which was basically checking like, is a label starting with a capital letter? If it is, then it's a cat. If it is not, then it's a dog. But from this chapter onwards, what we are going to do is we're not just going to classify dogs versus cats, but we're going to actually classify the pet breeds themselves. So let's do that. So we already have the data set. I'm just going to import. And from this point onward, again, everything becomes a bit more code heavy. So let me try and make more space and zoom in a little bit so everybody can, it's easier for everybody's screens. Okay, so then what we do is we're pretty much importing everything that we need from fastai.vision. And we've already looked at the untar data. So what untar data does is it returns a path. So let me check what path is returned. So untar data, if the urls.pets is a URL. So it's like a S3 AWS URL. This is where the data set sits in the internet, in the cloud. So what we could do is, what this untar data will do, unless this data set already exists at this path, what it's going to do is it's going to download it, and then it's going to untar the data at this specific folder. So in my case, this is home/aurora.fast.ai. In your case, this could be whatever username you have. So this would be a different path, but it will still sit in the .fast.ai directory in root. Something that would make a really nice blog post is to explain everything that goes on in untar data. And what you could do in that case is go for //untar data, have a look at this code. And trust me, by doing this exercise, you'll be a better coder than when you started without this exercise, because there's like so many good convenience functions in this untar data. There's a lot that's happening in untar data, which is really interesting. So anyway, I'm digressing a little bit. So that's what it does. It downloads that data set of the urls.pets, and so now this path has our data set. So if I have a look at this path and I can do path.ls, then I can see there's 2 folders, images and annotations. And one thing you'll realize is if we go to the website of this data set, what they'll say is the annotations contain information about where the pets are in the image. So it's not information like what the breed of the pet is, but it's information about where the location of the pet is in the image. So that particular kind of a problem is called segmentation, image segmentation, basically. But because for this chapter, all we want to do is we want to classify pets. We want to classify pets between the breeds. We're not going to be worried about this annotations folder. So if I go in the images folder, I could just say path/images, and I click ls, which just is like list whatever's inside this folder. So you can see that there's 7393 files over here, and you can see how all of these files are named either with a capital letter like this, or with a smaller letter, but it's really important to see how the data set is structured. So something you should focus here, I think the main point to focus from this point forward is we, as deep learning practitioners, we're going to be spending a lot of time on different kinds of data sets, and how data sets are actually structured is really important. Like, we need to work with different kinds of structures. So for example, just today I was looking at a Kaggle data set, which in one folder has 4 subfolders, and then the 4 subfolders have like different numbers of files. So I think the main challenge is working with these different kinds of data sets and how they're structured. So I guess from personal experience, what I want to say is you want to actually spend time on how your data set is structured first before digging your hands into modeling. And the next thing I want to specify is every time you do .ls, what it returns, so if you check the type of, let me just actually put this in output, and then that's the output. And if I check the type of this output, you can check it's a fastcore.foundation.l. And what this, so it's basically an L class. So these are things you should actually try on your own. And the reason why I wanted to just code in front of you and I wanted to show these things is so you can go back and experiment. So writing about .l or what this fast AI. So L is it's like a Python list, but it's supercharged. So it has a lot more convenience functions. So something you will see here is most functions and methods in FastAI return a collection that use a class called L. So if you really want to find another good topic for blog post, is this thing called L. So go in and check what this L is, and you will see how different it is from Python lists. So if this was a Python list, you could just actually convert it to a Python list. But see what's going to be different. When you click Python list, it's going to print all of the 7,393 basically everything in there. It's going to show in my Jupyter notebook. But look at this, it doesn't tell me how many numbers is, and that's what different about FastAI list is. It's really a convenience function which will tell you that's the total number of elements, and then it only shows the top 10, and it shows them separated by a comma. And there's other things you can do, like you can map functions easily. You can collect things easily. So anyway, so that's just a little bit again of a digression. And I'll keep doing that as we keep going in this chapter more and more. I will keep pointing at things that could also make wonderful blog posts. So writing about this foundation.l class from Fastcore is something that will be really, really handy. Okay, the next thing that you want to see and note here is we can't really, if I'm trying to find the label of my basically if I'm trying to find the label, then I can't really do like basically a separator by underscore, right? Like the first or the easiest thing that you could say is, okay, separate by underscore. So you pretty much get the name. So if I go output 0, so see that's that. And then because it's basically a Python path. So you might ask, okay, what's this path? So the next thing you want to check is what's this path. So search pathlib path. So pathlib path will show you exactly what this path object is, and it will show you. So these are the things how by learning more of FastAI, you'll also end up becoming a better coder, because then you have to know all of these things, and you become better at solving different problems. So that's how my journey started as well. But you'll see, then read about path, and you'll see like it has a lot of functions. One of the functions that it has is a name. So I could just check the name. So then that's the name. And if I really want to get my label, then the label is Persian, right? Because that's what the label is. So I could just say, okay, split this name by an underscore, and then grab the 0th element. So then it grabs me Persian. But if I try that for this, if I try the same thing for my output, the first output, and I do exactly the same thing, then see how that gives me just German, but the actual answer should have been German short-haired, because we want to also get this short-haired. So you can't really just split by underscore. You need to do something better. That's what this next paragraph will tell you. And so to do something better than what this paragraph will introduce you is to something called a regex. And then again, if it's, I do hope that many of you, because one of the requirements is like you've coded in your life and you have 1 years of experience of coding. But in case you don't, and you kind of struggling on understanding what these things are, just search regex, and then you can see how there's like all of these different cheat sheets. There's different websites that are built as tutorials to learn regex. And if you want to learn the Python version of it, you can just say regex Python, which will take you to the Python docs of this library called RE. It's just called RE. And then you could check what the syntax is, what it means. And basically, it's a library that can then be used to extract patterns from strings. So then that's the main thing that you will see as part of this paragraph. So we could actually then create a pattern. And what this pattern is, this pattern is telling us that we want to extract. So what it's basically saying is, what you want to do is you want to, after the underscore, you're going to have some digits. So /d in regex stands for digits. And plus means you're going to have more than one. And then after that, you're going to have the .jpg towards the end. So dollar in the end would, in this pattern, is trying to tell this regex is it's sort of a programming language on its own, but what it's trying to tell is, okay, my file is going to finish with the .jpg at the end. So this dollar just means like this is towards the end. I mean, this is the pattern .jpg, and before .jpg, you're going to have some digits. So let's see why that would work. So it's basically saying we're going to have some digits followed by .jpg. Okay, so we're going to have some digits followed by .jpg, and then we can extract everything before the underscore, which will give me Persian. Then over here as well, I'm gonna have some digits and then .jpg, so I could extract everything that's before, which means I'll grab German shorthand. Same thing for all of these. I'm gonna have some digits followed by .jpg, and then I can grab what the class is. So that's what this function is. So if I check, if I say basically I use this pattern on my remember what my output 0 was. Output 0. Did I miss something? It's called output. Okay. So my output 0 was this. I can try. The first thing I do is I grab the name attribute. So every time you do something like .name, that's the attribute of this part. So I can grab the name attribute, and then on this I can apply, instead of fname.name, I can find my regex.findAll, giving it a pattern, and let's see what it returns. Okay, it returns Persian, so it's able to grab the Persian. What about the first, like the German shorthand? This is where the underscore splitting didn't work for us, right? So let's try that here. Okay, it's able to grab German shorthand as well. So that's great. So these are small things that you should try on your end. And then a third topic that could be really helpful for a blog post is you'll find this regex is this undervalued Python tool that's really undervalued. So you could write about this and you could share it with the world as like, oh, hey guys, did you know about, like, you can find patterns just using this wonderful library. Okay, so I'm going to wrap up until pre-sizing, and then that's when I'm going to look at questions just in case anybody's. So this is the last thing then. So we looked at this in chapter 1. Now I can create my data block. So in FastAI, you have this thing called data block, which is like a framework for the task that you're trying to do. So the task that we're trying to do is image classification. So you can pass in 2 blocks, which is the image block. So the first block is for your X, and the second block is for your variable Y. So the first block is the images that you have that you want to classify, and the second block is the labels. So basically, okay, if you want to classify, then what is the label corresponding to each image? So based on the 2 things, you pass in 2 blocks. So image block will be for creating the images from these parts. So basically this pets data block will it will basically take in all of these outputs, which are just path. And then from these paths, it will extract images. And from these paths, it will extract labels. So that's exactly what goes on in this data block. And then all you have to do is you have to define a way, or you have to give FastAI a framework. Is like, okay, how is it going to extract the images from these path 7393 paths, and then how is it going to extract the labels from these paths? So this is the basically framework. So what it's saying is, okay, you get items by using get image files. So if you pass in a path/images, and you say get image files, passing in this path, see how that returns all my image files. So instead of 7393, get image files will just return everything that's an image or ending in like .jpg or other things. We've looked at this function before. So then these 7390 items will go in, and then you say, okay, from this, can you please extract my X, or from the image using image block, and you can extract my label using category block. So that's the main framework. Then you say, okay, can you split my data set into training and validation using something called a random splitter? So I've already looked at random splitter, but you could just pass into a random splitter some numbers, and it will split it into it will basically split into a validation and training set. So that's what this will do, is it will use the random splitter to basically split things into a training and validation set. And then you could say, okay, how are you going to get my labels, FastAI? You're going to use my regex labeler. So for everything, the first thing you're going to do is you're going to extract the name attribute from this all of these items. So for the first item, for example, if I say these are my items, and then my item 0 is this, and then for every one of these items, you're going to grab the name attribute. And when you grab the name attribute, then please apply this something called a regex labeler. So let's see what happens if I apply that to this. So let's see regex labeler, and I can pass in my item. Okay, great. It basically is able to grab the label from the path. So see, this is how you get your Ys in Datablock. The get Y is going to grab the label or the name of the pet breed just by using this. And then you say, okay, once you have your images and once you have your basically labels, then please resize all my images to this size 460. What that basically means is like, remember how I did say in the past, is like in data loader, you want all your images to be the same size. And then finally, you pass your batch transforms, and these are the augmentations. So augmentations with things like rotation or things like zooming in, zooming out, or all that stuff, so your model becomes better at generalizing. So we've looked at this in the past as well, and that's how you get your data loaders. So you could then say dls dot show batch, and that's it. I've created my data set. So see how every X or everything becomes an image from the path. It's applying augmentations, and then it's able to show me the labels, and that's basically it. So that's the main bits. So let me go and have a look at some questions if there are any. Can we just upload the unzipped data set to the notebook and change the directory and then access the training data? Yes, you can. Then you'll have to basically then, yeah, you just update your path to be that specific path. You can definitely do this. Also, I came across this term called environment, specifically creating a Conda environment using Miniconda. I request you to please explain how to set up environment and why we need to do that. Okay, thanks, Prabhav. That is a good question, but slightly out of context. That's something I will look at when, I will look at this when we, yeah, outside after, I'll look at this and do it on Slack. So I'll answer this, but on Slack. X is input, Y is target. Yes, that is absolutely correct. There are some use cases where we require creating data block with more than 2 blocks. Is that even possible? Okay, thanks, Gaurav, for a good question. This is something, again, we will look into later, but you know, you could have basically for object detection, you could have a classification, and then you could also have the label, basically the bounding box locations, or like you could have a mask, and then depending on how many things you want to do. So this is just something that's again separate and looking far ahead. So this is again something we will look at after. Instead of regex labeler, I assume, can we define lambda like this? Yeah, please have a try and see if that works. I don't think like, as long as your pattern or as long as your function is able to extract the, like basically as long as your function is able to extract the correct label from the path, then you're fine. So go for it. Why are we doing resizing 2 times, first with 460 and then 224? That's a really good question. That's exactly something that we're going to look at straight after this. Is it recommended to work on image classification on Scratch like in chapter 4? Yes, it's definitely recommended, and it's definitely something that we do want to do more and more of. But to do things from scratch, we need to first understand things. And as part of this chapter, then we're going to understand things, and we're going to look at them, and basically going to dig deeper and deeper every chapter. So you will get to a point where you'll be able to do things from scratch. What if we use the trained weights from someone who trained properly on MS Coco? MS Coco is again an object detection data set, so I'm not sure if I get the question. So I'll give you a minute, Prabhav. Could you please comment and let me know if what that question is? Okay, maybe I put you on the spot. I'll come back to this then. Okay, so then some good questions like why are we doing resizing twice? So why are we basically doing something like a resize 460 and then we're doing augmentation transforms for size 224? And that's exactly what our next topic, presizing, is. So let me give you a gist of presizing. I'll only give you a summary, and then when you go back and you read this part of the book or this part of the chapter, it will all make a lot of sense. So something that you will see in FastAI, something that happens is you will have all of these different images of different size. Some are going to be rectangles, some are going to be vertical rectangles, some are going to be basically you're going to have all of these like in your data sets. You don't always get everything that's like ImageNet data set that's like clean or everything's the same size. You never get that in the real world. So say if you're trying to do property classification, then you get data sets that some images could be like really, really small, 128 by 128, or even not even a square, or some images could be really, really large quality depending on. So I think there's a deeper thing to understand before understanding this part. It's like when you're creating data sets in deep learning, you're trying to collate information from a lot of different things. So if you're trying to create a medical data set, it might be so that you're getting the data from a lot of different medical institutes in the world. And then each medical institute might have a different camera or might have a different device that it uses to create your data set, which means you're going to get in your final data set or your massive data set, you're going to get this the images or whatever your data set type is, you're going to get all of these different versions. So they're going to be all different sizes. But if we want to make the most of GPU, or we want to create our data loader in PyTorch, then we want all of our images to be first squares, and then B, we want all of them to be of the same size. So that's why we do the resizing and we do the augmentation. So one thing you will see is when you do augmentations, like again, why do we do augmentations? We do augmentations like random cropping, rotating the image, inverting the image, flipping the image. We do all of these things so that our model is able to learn different versions. So this bear, if you see this bear in if you're trying to build a bear classifier, then you're not always going to get the bear that looks basically like this. Maybe the bear could be not from right to left, like going left to right, so it could be inverted, or it could be like at a different angle, or the basically your camera could be at a different perspective, so you could be taking the image from the right, or you could be taking the image from the left. So you want your model to be able to generalize to all of these positions. And that's why you add augmentations. So that's the basic idea of why you add augmentations. But then what happens is, and I'm basically what I'm doing right now is I'm explaining everything that's about this presizing chapter. So you can go back, and when you read this, it will make sense. And then what happens is when you are doing augmentations, so in augmentation, you're trying to rotate the image, or you're trying to flip it, or you're doing all of these different things that you want to do to the image. Then the size of the image could change, right? So say, where am I? Let's try this. Let's say I have my image. First, let's say I had my whole data set, and I resize everything to be, say, 224 by 224. Now, when I'm applying augmentation, so this is, let's say this is my bear in the center. Now, when I'm trying to do rotate, and then say I rotate it, so that means that that's how the bear looks like. And then what's going to happen is, like, on the edges, what's going to be there on the edges? These are all going to be blanks, or like these are all going to look different. So like there's going to be corruption in your image. So one thing that FastAI does is, what they first do is they resize everything to a much larger image size than what you want to work on. So you resize everything to first 460 by 460. So that's the first step. So let's say you resize everything to a much bigger size. So that's where your bear is in the center. And then you do your rotations, your augmentations, everything in one go. So now every augmentation is happening in one go. So say that's your basically rotation. And now, even if you don't have the edges, it's still going to be corrupted on the edges or something. But then, because this size is 460 by 460, then you do the random crop. So then you grab the 2 to 4 by 2 to 4 image. So that's why you have two resizing, or you have two, somebody asked that question in the comments. It's like, why do we have two resizing? So this is the reason why we have two resizes in FastAI. So that's what is going on. And then you can see in this example, on the left is how FastAI deals with this bare image. So both of them are resizing the image to 2 to 4 by 2 to 4. And on the right is how FastAI says other libraries do it. So you can see how on the edges, FastAI has still got these edges intact. It still looks like everything, and then you still have grass on the top left. But if you see on the right on how other libraries do it, is like you will see, okay, there's no grass here because you're trying to rotate it so that grass is gone. And then there's like more corruption on your bottom left and all that stuff. So that's the main idea of this pre-sizing. So I'm gonna, so that's what FastAI says, is like it does things differently, and then it does all the augmentations in one go. So your image looks a bit more sharper than generally what you will see. Okay, so then you can, once we had our data loaded, then we could pretty much click show batch. But then the next thing is like debugging and checking a data block. So far I told you, like, data block is this framework of defining the problem that you're working on, and it's a framework to tell FastAI, is like, oh, hey, FastAI, I'm working on image classification. I want you to get the labels using a regex labeler. I want you to use the attribute name from my paths before applying the regex labeler. I want you to randomly split my images into a training and validation set. So a data block is basically just that framework that's telling FastAI to do things a certain way. But many a time you'll find is like when you're trying to build a data block for new different data sets, you're going to encounter lots of errors. So what you could do in that case, so let's say I'm trying to build a data block, but what's missing here is I missed the resize operation. Okay, so ideally there should have been a resize operation like this as well, right? Because that's when every image becomes the same size. But let's say I missed it and I click enter. So it builds it, but you can see how there's like this error. So in pets, you could say basically for every data block, you could say summary. And if you print out that summary will look like this, and it will show you, okay, this is where that error is coming from. So it will make things really easy for you to debug. So you could have a look at, okay, I'm first setting up my pipelines, then this is exactly, I'm applying basically creating an image from my path, which is, this is what the path looks like for one item. And then I'm trying to apply the categorize function to this. So if I apply the categorize function to this, it gives me basically the American Bulldog as the label, and the category is category 12, which is what the model knows it as, because your model won't know American Bulldog, right? The model needs numbers. So American Bulldog gets converted to number 12, and that's what the model knows. And then finally, your PIL image. PIL is again pillow, which we spoke about last time. And then that's what your image is. So basically, what I'm trying to say is then this data block.summary is a really, really handy function call that will help you debug any future questions or any future problems that you'll see. Excellent. We're really on track. And now I could create my, basically, once I have my data loader. So something I want to show is like, for any point, if your DLs.showBatch works, at that point, you should be really happy. You should open a bottle of champagne, not literally, but you should be really happy because you've done the hard work. And then to create your classifier, all you do is you create your learner first, which is your model. So this is your convolution neural network, passing in my data loaders, passing in my model, which is ResNet 34. And then I say my metric is error rate. And then you could just say fine tune and your model is training. This is something we saw in chapter 1. So the hard bit or the hard things that you'll find going forward is this DLs dot show batch. So once you get it to work for your own data sets, that's when you're like, sigh of relief, cool, well done, and let's create the model now. Okay, so that's that. So let me have a look at questions again before. So that was basically, that was like why we have two resizing in this section. And then this section, I also showed you basically how you can debug your data loaders going forward. So now we're going to start with cross entropy loss straight after I answer some questions. Okay, what if we use the train weights from someone who trained? I mean to ask, can we really avoid building from scratch? Yes, that's what transfer learning is for. In transfer learning, you're trying to resize and you're trying to reuse all the weights. So yes, the answer is 100% yes. Is there a risk to overfit if we have too many augmentations from the same image? Alina, first of all, please post the questions in the comments. Thanks, Angelica, for doing all the hard work. But without pointing anybody out, Angelica shouldn't do all this hard work. So Angelica, going forward, maybe just skip the questions if they're in the Zoom chat. But second, if we have too many augmentations from the same image, then is there a risk of overfitting? If you have too many augmentations, then what you're actually trying to do is you're trying to avoid overfitting. So augmentations actually exist for the opposite reason of overfitting. Because when you're trying to corrupt your image, or you're trying to rotate it, or you're trying to like invert it, so every epoch, the model sees a new version of the same object, which means the model never actually overfits. So this is actually, the more augmentations you have, you're actually going away from overfitting. So hopefully that helps. Alan, does random crop create problems with multi-label image learning? What if the crop does not contain one or more items of the label, items labeled for that image? Good question. We haven't looked at multi-label image learning so far, so let's not confuse everybody. So everybody shut your ears, but I'll still answer this question because Alan asked it. That's okay if the first epoch doesn't contain all the labels. In the second epoch, a different random crop would be selected, which means you will select a different part of the image, which means then that might have the second label, or that might have both the labels. And then in your third epoch, you again have a separate random crop. Karthik, it's a bit counterintuitive to me how fast AI presizing has better accuracy. Like Aman said, it would result in a sharper image because we're padding the edges of the image and then cropping. In my opinion, though, this would also lead to lesser diversity in image resolution. Karthik, this is a good point that you're raising, but I think this is a good experiment. Again, go and try and run lots of experiments and see why fast AI, rather than believing me. Have a look and try your own experiments. And if you do come up with an experiment where fast AI has less diversity than a standard PyTorch data loader, then you've actually contributed to the fast AI community a lot more, in the sense that you've pointed fast AI, you've pointed to the creators of fast AI that something is missing in the library, something doesn't work the way you think it does, and then you've actually pointed out a problem. So again, that's a really good experiment for you to try. Prabhav, how do we train the model and detect the object which are partially visible? Again, I think we're digressing a little bit. Detect the object which is partially visible occlusion. I think what you're trying to say is like the image is corrupted on its own. Well, then if your data set and your image is corrupted on its own, then the model can't really learn a lot. I mean, it can, if there's other images of the same class, then it can learn from that other class. But if your data set is corrupt, then you can't really help. You try and get a better data set that has all the objects visible in the images, at least. Because again, something we looked at with deep learning is like the model is learning what you give it. So if you give it good data, it learns good representations of that data. If you give it corrupt data, then the model learns corrupt things. So your model is only as good as the data you feed it. Okay, going back to cross entropy loss. Cool. So this is the most interesting part of this whole chapter, in my opinion. This is where we look at cross entropy loss. Until I read this chapter, I never saw cross entropy loss the way I did for this chapter. And yeah, it's just a different perspective. It's just a different opinion of how you look at cross entropy loss. So now we already have the data loader, right? So we can just grab the first batch. So let's see what my X is. Length X, it's 64. Can I check X dot shape? Okay, so every part has first been converted into an image, and then it's been converted into a 3-channel, because images have 3 channels, red, green, and blue. It's been converted into 3 channels, and then it's been converted into 224 by 224 image. And then I have my labels. So everything then grabs a label, right? So this is, remember how for a path, we first converted everything into like grabbing the pet name. And then from that pet name, we converted everything into a category. So this is what this tensor category looks like. So you have your Y's are basically these categories, and your X are basically those tensors, which are representations of the image. So we can grab the predictions. It says my learn is not defined, so I missed this bit. So I have to fine tune it and have to train it. So this is going to take 40 seconds, but that's okay. I will repeat what we're doing so far. It's like I created my learner, I trained my model on the data loader that I created, which is I'm training my model to do pet classification. And then I'm just trying to grab the prediction. So once this works, which will take another 20 seconds, let's see if there's any more questions so far. I tried progressive resizing. Thanks, Adriano. That's a really, really good question, but we haven't really looked at progressive resizing so far. So I'll answer this, but after the session. I think it's a really, really good idea. So please go for it. If you feel it gives you better accuracy, I'm very for it, and you should definitely try. So you can see how just by doing these few steps, we are able to create like a learner that has an error rate of 0.09, which means it has about 91% accuracy. Actually, that error rate came down to 0.7, which means the accuracy is about 93%. So this this ResNet 34 model is able to classify the pets to its actual pet breed with 93% accuracy, which is really, really high, or really, really good. So now, let's say I pass in my X and Y's and I'm trying to get the predictions. So I get my predictions. Remember our batch size was 64 because that's how many, again, we looked at batch size last time. So we basically convert the data set into batches. So my first mini batch had 64 items. And for those 64 items, these are the labels. But I also get the preds, right? So if I check the preds dot shape, it's actually 64 by 37. So this is where things are different than the MNIST classifier that we were building last time. And this is when, because you have 37 labels, basically your model is predicting a number for each of the 37 categories. This is important. I'll repeat this again. When you do predictions in deep learning, or basically when you call or do a forward pass on the model and you pass in new images, then the model predicts some number, which is called activation. So the model predicts some number, or the output or activation, final activation. It predicts that number for each of the categories. So in our case, because we have 37 categories, it's predicting a number for each of the 37 categories. That's the output. And the best part is, if you do the sum, if you basically calculate the sum of these 37 numbers, it is 1. So you could treat these 37 numbers as probabilities. So the probability that the prediction is the first category is 0.01. The probability that the prediction is the last category is 0.0005. So it's really, really small. So that's what these numbers can be interpreted as. Because they sum up to 1, you could actually treat them, like you could actually think of them as probabilities. Now, why do they sum up to 1? That's the question, is like, how is my model always able to, like, even if I would have gone for the next batch, then again, the numbers would have still, so let me do that actually. Preds 1, instead of looking at the preds 0 at the preds, I can then check the sum. So if I check the sum, it's still 1. So exactly why, like why do every predictions for each of the 37 categories sum up to 1? It's thanks to a function called softmax. And we apply the softmax function exactly after the final outputs from the model. And what this softmax function does is it converts every prediction into this sort of a probability that all predictions sum up to 1. And how exactly does it work? We looked at sigmoid last time. So remember how this sigmoid function looked like. So if you have really big numbers, they'll be closer to 1. If you have really small numbers, they'll be closer to 0. So let's say we're going back to a problem of classifying 3s versus 7s, and the final activations from, and this is without the softmax so far, the final outputs that we get from the model are like this. Okay, so these are the final outputs, and because these are just outputs from the model, they could be positive, they could be negative, because you're actually doing matrix multiplication. So you could have positive and negative numbers as outputs from the final layer of the model, basically. And for each of the category, you get a prediction. So let's say the first one is for digit 3, and the second one is for digit 7. So these are just some numbers. So right now, these numbers don't mean anything, like just like it doesn't matter if they're positive or it doesn't matter if they're negative. Like what I'm trying to say is these are just some numbers that we can't really look at and say, oh, the model's 67% confident or the model's 25% confident, because they don't sum up to 1. So if you apply the sigmoid operation, which we looked at last week, you can't really then convert all of these numbers to between 0 and 1 because they don't add up to 1. Right? If you do the sigmoid, then 0.6 plus 0.5 is 1.1. Or if we do something like 0.7 plus 0.6, that's 1.3. So they don't sum up to 1 yet. So you can't really interpret them in a way of like, probabilities yet. But the important part is the model, like the model is actually trying to tell you is like, because the magnitude of this number is higher than the magnitude of this number, which means the model's actually more saying that this number, remember, because we said the first column is for 3 and the second column is for digit 7. The model's actually saying that for this row, the item that I was fed is more like a 3 than a 7. So instead, what I could do is I could take what matters is the difference between these two numbers. So like if this number is incredibly higher than this number, then that means the model is really, really confident that this number is the first category, which is what is the case like for this activation or for this output from the model. Because this is 4.4 and this is minus 1.2, which means that the model is saying, I'm very confident that this is the first category or the digit 3. So what matters is the difference between these two numbers. Okay, so I could actually take the difference. So if my acts is like this matrix, then I could grab the first column and I could take the difference with the second column and I could then call the sigmoid operation. So now what this number means is like I am 0.9966 or like really, really confident that this prediction for this row, because that's the fourth element, right? This is what the fourth element is. What it's trying to say is that for this prediction, I'm 0.99% or like 0.99 confident, like that this number is a 3, because we've now taken the difference sigmoid. We haven't really just turned every number into a sigmoid. So this difference matters. And then if this is the probability of the number being the first column, because remember we took the difference of like first column minus second column. So the sigmoids that we get are the probabilities of the final answer being the first column. So like for the first one, it says 0.6 confident, 0.5 confident, 0.9 confident, 0.3 confident, which means the probability of it being the second column is 1 minus this number. So that's my first column. And that's my second column. So the probability of these things being a 7 is really high for this one, because it's really low for basically that. So I think that's just the basics of it. And that's exactly what softmax does. So softmax, instead of just doing like a probability of like 2 classes of like 3s versus 7, softmax does this for every class. So if I take in softmax, I could then just pass in my activations, which remember look like this. So I could just pass them to softmax, and if I call them softmax activations, and you can see how the output, or like the first column, matches this. Okay, so that's in a way the probability of the number being a 3, because we said the first column is digit 3, and the second column is basically these numbers, which is exactly those numbers, 0.3975, 0.3975. So that's what softmax does. And the mathematical way of looking at softmax is the exponential. So you convert. So what you have is, how do you calculate the softmax in maths, or like the way to do it for all categories is like, say I have 3 categories, Teddy, Grizzly, and Brown, and the outputs from the models are 0.02, minus 2.49, 1.25. Then you take the exponential of these, which means e to the power 0.02, e to the power minus 0.249, and you get the outputs. Then you sum them up and you divide all of these by the sum. So now the sum of these numbers would be 1, which means that the model's now 0.76, which could be treated as a probability. The model saying that it's 0.76% sure, or like 76% sure that the prediction is brown. It's much easier to interpret the softmaxed outputs than it is to interpret the outputs. So that's the softmax function. Let's see if there's any questions. I tried. So when we again, Lalit, please post the questions here in the forums. Thanks, Angelica, for copying them from the Zoom chat. When we do backprop, we need gradients, right? But then some activations like ReLU are continuous but not differentiable. How does backprop work in these cases? So I'm going to skip this question, but again, this is different from what we're looking at right now. We're doing softmax, and we're doing there's lots of good articles written about what a nonlinearity does. But when you say ReLU is not differentiable, I think that's where you're kind of wrong. So I have a look and confirm that ReLU is not differentiable. It has confused me that we think of the output after softmax as percentages. It seems to me like the function would throw off any percentages that are being used. Is it really a percentage after the softmax? That's a good question, Kevin. I actually still, while I was calling it percentages, it's just a bunch of numbers that add up to 1. So I don't mind interpreting that as a probability or as a percentage. But again, that's just something that's in my opinion. It could be, yeah, it could be different than that. Like I could be wrong, but I don't mind treating them as probabilities. I hope that helps. I see that you have the link for the Kaggle COVID-19 competition. Oh, where is it? I didn't see it, but yeah, it must be in the Google Chrome. I was just having a look and trying at things. As a follow-up to Kevin's question, could we interpret any activation that's squished the outputs as a probability, or does softmax have other good qualities about it? Softmax really wants to pick a thing. So what softmax trying to do is, it's trying to, when you take the exponential, then positive numbers, when you take the exponential of positive numbers, then they become even more positive. And when you take the exponential of negative numbers, then they become really small. So what softmax in a way is doing is it's increasing the difference between the model's predictions. And what softmax is then trying to do is it really wants to pick a thing. But as I said, I don't mind treating them as, like, I don't mind treating the softmax activations as probabilities, but don't quote me for it. I could be wrong. For using full MNIST, isn't it better to use cross entropy loss that MNIST loss based on envelope loss? So we are actually just starting to look into cross entropy loss. But for full MNIST data set, yes. So that's where we headed, Korean. That's exactly where we headed. Okay. So then again, a summary is like, what's the difference in this part is like, you get basically a prediction for each as many categories as you have, that's as many predictions as you get. So right now, because we're doing 3s versus 7s, it's okay to have like the first column representing the digit 3 and the second column representing the digit 7. But we saw that for pets, we get 37 predictions for every row or for every item. And then softmax is that thing that converts like the final raw outputs to something that I do believe could be treated as probabilities, but again, could be wrong. Okay, so now we headed towards log likelihood. All right, so at this point, let's assume that my targets, because we're doing 3s versus 7s, right? Let's assume that my targets are this 0, 1, 0, 1. So this is just target saying like, is the digit a 3? So 0 or 1 basically is the digit a 3. And then remember that my activations look like this, right? These are the softmaxed activations. So they look something like this, where the first column was for digit 3 and the second column was for digit 7. Now, basically, in PyTorch, you have something called as tensor indexing. So what I could actually do, what we really care about is the prediction of the actual target, right? So in this case, between the two numbers, what matters to, because the second number is basically just the 1 minus the first number, right? But if these were like even 10 columns, what would matter is the softmaxed activation, or I'm just going to call it probability again. What's going to matter is like, what is the model saying is the probability of the thing being the actual class. So because in the first row, the target is 0, which means between these two, this number matters to me. In the second row, because the target is 1, what matters to me is this number. In the third row, because the target is 0, what matters to me is this number. So I really want this number, or every number corresponding to the true label, be as close as possible to 1, because that just means that now the model is really confident in always predicting the right class. And because as high as this number is, then the other numbers are going to be lower, because they always sum up to 1, and the other numbers are just going to be 1 minus the actual label. Okay, so how does this tensor indexing work? Like, why can you just pass in an index and why can you pass in a target? So this is what's been explained in this part of the book. Is like, you have these predictions. So the first thing corresponded to a 3, the second thing corresponded to a 7. Then you have an index for each of these rows from 0 to 5, and these are the targets, right? But for this matrix, the 0.0 would give me this item. The 1.1 would give me this item. The 2.0 would give me this. So you can actually index into this matrix, which was some acts, I think. So I could actually say 2.0, which would return my tensor, this one, so which is corresponding to the index and target. If I say 3.1, then that should give me that number 0.003. So which it does. So basically then all I'm trying to say is the way tensor indexing works in PyTorch is like, you have these index and you have the target, and then you can actually just pass in the index, pass in the target, and it will grab that particular item based on the target. And this is something that won't just work for binary labels. This is something that will work for as many categories as you have. So even if you have like 37 categories, and then these targets are numbers between 0 and 36, because 0 being the first item and 36 being the last category, you could still do this tensor indexing. So I guess at this point, then when we have our softmax activations, then what matters is the label is the number corresponding to the actual label. So I can still use this tensor indexing method without the minus so far. I could say that use this tensor indexing method and grab the prediction from the model that that's basically corresponding to the correct label. And then you just take a negative, and this is called in PyTorch, basically you have a function with this which is called negative log likelihood. Now, even though the name, like this is these 1, 2, 3, 4 sections are the only sections that are a little bit math heavy or a little bit more complex than all the other sections. But then what I'm trying to say is in PyTorch, you have this negative log likelihood loss function, which does exactly this bit. It's like it will first take the softmax of the, it will basically take the softmax activations, and then it will grab the item that's corresponding to the correct label. And then all it does is it takes the negative. So why is it taking a negative? Like, why is it just not positive numbers like this, which is what we did in the first place over here? Why is there a negative over here? The reason why there's a negative is because the NNL loss, or the negative log likelihood loss in PyTorch, expects that after the sum activations or softmax activations, what you're going to do is you're going to take the log. So the way PyTorch expects this to happen is like, the first thing you have is you have your activations, which are like, say, 2 columns and some rows. Then you take the softmax, then you take the log of these, and then you take the negative log likelihood loss, which is grabbing the number corresponding to the correct label. So this is how PyTorch expects things to be in this order. So I'm just going to say how PyTorch expects things. But actually, what we did was we just took the softmax and then we applied the NNL. So that's why you just have to say minus. But then a question you might ask is, why do we need to take the log, right? Why do we take a log in this case? So that's what we'll look at in this thing. So the reason why you want to take a log, and this is really, really important, is log has some really nice properties, but where am I? Where does it say things? Okay, it doesn't, I'm trying to find a specific line. Okay, here it is. So when you converted things to like these softmax activations, so this is 0.6, this is 0.39, this is 0.5, this is 0.49. Then without taking the log, what's going to happen is that our model is not going to care if the final softmax activation is 0.99 or 0.99. Like, if you think of it, 0.999, even though the difference between these two is very small, if you think of it, like, the model is actually 10 times more confident when it's predicting something with a probability or a softmax output of 0.999 versus when it's predicting something with 0.99. Okay, so let me try and explain things here. So we had the softmax outputs. This is for digit 3, this is for digit 7. Let's say these are just some numbers which both add up to 1. So 0.6, 0.4, 0.999, 0.001, and then 0.99 and 0.01. Okay, let's say I just had 3 items and these are the softmaxed outputs. So I'm just going to call it softmaxed activations. Okay, then if my loss, so what could my loss be? My loss could, if my labels are, say, in this case, the thing is a 3. In this case, the thing is again a 3. And in this case, let's say again, it's a 3. Then my loss could be, you just grab these numbers and that becomes your loss, because you just care about the numbers that are corresponding to the true label. So that could be the negative log likelihood, right? But if you just pass these numbers and then you take the loss, then for this row, the loss is going to be 0.99, and then this is going to be 0.99. But at this point, the model, that's a very similar loss, right? Having a loss as 0.99 or having a loss as 0.999 is a very similar loss. So what you do is you add a log operation. And what log operation does is, for numbers between 0 and 1, it turns things into 0 and minus infinity. So you basically, because we already have all our predictions between 0 and 1, right? So all our predictions are always going to be between 0 and 1. So what you do is you take the log of these predictions, which means it's going to convert things, and then it's going to be, then you get numbers where these and these two are different because you've taken the log, right? So it in this case, then when you take the log, that's when there's a difference between 0.99 and 0.999. So that's why you want to take the log. And remember when I said the negative log likelihood expects things to be negative, or like, why did we have to take the negative here? Is because the log is going to convert every positive number between 0 and 1, because all our numbers are going to be between 0 and 1. It's going to convert every positive number between 0 and 1 to a negative number. So you want the negative log likelihood like this. Then once you take the log, then let's say you have negative, 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 negative. All your numbers are negative, right? So to get a loss, then this negative log likelihood, because it's expecting negative numbers, that's the reason why we had to do minus some acts over here, just to have the same output as PyTorch. So that's the reason why you take the log. So the overall step is, you have your softmax activations, then you take the log, and then you take the NNL, basically the negative log likelihood. And all of these things together is your cross entropy loss. So that's cross entropy loss. So you can see how in PyTorch, you can say nn.cross entropy, and then you can pass in your activations. So in PyTorch, you always have two ways of doing things. Either it's through a class, or so this is how you can create the loss. But the second way of doing things is by using the f.cross entropy function. But they both give the same output. But in most of the docs, you'll find this version of the cross entropy loss being used, which is the class version. So that's the one that FastAI will also use in all its source code. But then you could then actually calculate the then you could actually calculate the cross entropy loss for each of your activations. So remember, your activations with this and your targets with these numbers, right? So you have 1, 2, 3, 4, 5, 6. So if you say in PyTorch, the reduction equals to none, then it returns a loss for each of the rows. And what it is doing is it's first taking the softmax of these, it's first taking the softmax, then it's taking the log, and then it's calling the NNL loss, passing in the target. So see how that gives the same number. And you could just say reduce equals none, I think. No, reduce equals union bool reduction. How do I make, oh, here it is, reduction. I just have to say reduction equals none. So see how that's the same as doing this. So NN dot cross entropy loss is actually, you first take the softmax of the activations, then you take the log, and then you pass this, you basically take the number that's corresponding to the target, which is what f.nl loss will do, and passing in reduction equals to none. If you don't say reduction equals to none, then it just takes the mean of all the rows. So if you want the loss, if you don't say that, then it just takes the mean of those numbers. But if you say reduction equals to none, then it returns the loss corresponding to every row. So that's what cross entropy loss is, my friends. I know this could be a little bit complex when you do it the first time, but when you go back, re-watch this section of the video and read this part of the book, I think it will all make a lot of sense. So let's see if there's any questions so far. For using the full MNIST data set, isn't it better? Okay, this is the one I saw last time. So now I think, Korean, I hope this helps on why cross entropy loss is used for multiple categories. And, I hope this explains the difference between this cross entropy loss and the MNIST loss that we saw last time. Excellent. Kevin, that's a really, really good point, that it would be really interesting to see if there's another way of like converting the activations to between 0 and 1, because that's essentially what you want to do. Because if numbers are between 0 and 1 and you take the log, then it just magnifies the difference between those numbers and it converts everything to a negative number. Do we want to use the logarithmic function to amplify the value since the incremental improvements are significant? Yes, so that's the point of like, that's the logarithmic function. We do it because if we didn't do it, then the difference between 0.99 and 0.99 wouldn't be considered a lot by the model. So that's why we take the difference. So let's actually do it. Let's see torch.log, and let's see what the number is for 0.99. So that's the number. And then what about 0.999? Okay, so that's again 2 decimal things. At least that's what the book says. It's like, then this difference between them is highlighted. So see how this number is 10 times bigger than this number, right? Because that's exactly what's going on. So this number then becomes 10 times bigger, which means now the difference between these two numbers is not 0.0009, which is a very small difference, but the difference is actually of that of 1 decimal place. Or like this, now you know that this model is, sorry, I said things the wrong way. What I meant to say is like, this number is 10 times bigger because it's less negative. So this this number corresponding to the log of 0.999 is 10 times bigger than this smaller number. So that's why you take the log. Is like, now you know that when a model predicts something with 0.999, it's just 10 times more confident than when the model predicts something with 0.99. So that's that. Okay, so I think that's all the questions. Yes, that's why we take the log. Yes, you've got this, Prabhav. Cool. So that's the cross entropy loss. After this, there's model interpretation. So I'm going to wrap up after model interpretation, and we'll look at learning rate finder and the rest. So I did say I was very optimistic that I'll finish this chapter, and then we'll get to the questionnaire. Looks like that hasn't happened. But in model interpretation, then what you want to do is, because you have these 37 categories, right? You have 37 categories. You could actually create a classification or like a confusion matrix by using classification interpretation. So you could just say, if you want to interpret how good your model is, then you could just say, create this class classification interpretation, and you could pass in your learner. And then you could just say, okay, plot confusion matrix, and you just say my figure size is blah. And then that's when you see how your model is doing. So you can see for 3 items, even though the true label is ragdoll, the model predicts something as a Persian. So like you can now interpret how your model's doing, basically. And then you could say interpret dot most confused. So the model is actually the most confused between American Pit Bull Terrier and Staffordshire Bull Terrier. So let's see why the models. Actually, this is something I even don't know. Okay, so that's what an American Pit Bull Terrier looks like. And then what about a Staffordshire Bull Terrier? Oh, are they very similar looking dogs? So that's American Pit Bull. Okay, and then Staffordshire is this. Yeah, they kind of. I mean, I do agree. They kind of like the fur is similar, and they're kind of the same looking dogs. And it does make sense that the models are a bit more confused between these two because they're very similar looking. I would be very surprised if the model was most confused between a cat and a dog. So that's it. So that's where we're gonna wrap things up today. After this, we're going to do we're going to look at steps and what we can do to improve our model. And we're going to wrap up chapter 5. But something I do want to ask everybody to do is like look at those 3 things that I did say for blog ideas, which was one of them was rejects. I think the second one was about the fast AI list. And you could actually also look at cross entropy loss and write about that. So I think that's the 4th. I'm missing what the 3rd was. I've forgotten what the 3rd thing was. But let's see, there's one last question. Will you be taking the environment set apart on Slack? Yes, probably I will be. So I'll get back to you on Slack with the environment set up. So thanks everybody. Thanks for joining me today. Next week we'll wrap up chapter 5 and we'll start with chapter 6. See you guys next week.